So in this video, we are going to consider the calculations which are on our condensers. The condensers are very, very important in our syllabus as we have got a lot of changes in our curriculum. So we need to add some of the things that we can consider as we are doing our calculations. From the introduction video, I stated the basics that you need when you are to deal with a steam condenser and also the types that we have on our steam condensers, which also will influence on our calculations. And also, I mentioned the issue of inconsistency in terms of formulas, calculations that are being used. You check this calculation from your textbook, you check another textbook, you see different uh, point of view on those calculations. So I'm going to just bring up a general or an overall view that we are going to use as long we are dealing with with condensers, and that is going to guarantee you that you are going to have all your marks, all right, all the marks that are there, because we just need the basics. So this video is meant for us to gather the information and also correct some of the other things or mistakes that you have been seeing in our question papers. You see a calculation that you see, no, this one does not even match to what I have been taught before. All right, so as part of your calculations, the first thing that we will need on our condensers is to understand the pressures. Remember, we said it deals conversion of pressure. Okay, so definitely there is a need for us to understand on our calculations the pressure concept of the condenser. So the condenser pressure, um, there are so many things that we need to consider before we go to the absolute pressure, which are the gauge pressure. All right, so let's say we can have the gauge pressure from what? From the manometer reading. Remember, we're dealing with the gauge. So the gauge pressure is taken from the manometer reading. So that is given as what? As PG from the manometer reading. So PG is given as we're going to have our density times the gravitational acceleration times the height that we consider. When you consider the height in the gauge, like the manometer, that's a manometer reading. All right, so that is the manometer reading, which before we used to write it as m like this for the manometer reading. All right, so this time we're gonna use HM. So HM, wherever we see that, we just consider the guys that we used to in our old syllabus manometer reading. It is just one and the same thing. All right, so there we are calculating the gauge pressure in what? In pascals. So it can be in kilopascals. You can leave your answer in pascals as it is. All right, density, gravitational acceleration, then the reading of the manometer. So this one is our manometer reading. The gauge reading. All right. So it is representing how high the mercury is. How high. So that is taken in millimeter mercury. The unit will be millimeter mercury, because we are dealing with the height of the mercury. So it's millimeter mercury that we're going to have. Millimeters of what? Of mercury. For the gauge pressure, you use what? The manometer reading, because there is another one that also we are going to use with the same concept of the formula, but this time it is the atmospheric pressure. Atmospheric pressure. So whenever we are dealing with the atmospheric pressure, that is P, you can have as PA, depending with your textbook, you can even write as P atmosphere, like ATM. Like I said, same concept. But as for the atmospheric pressure, it is taken from the barometer reading, this one. From the barometer reading. We used to write our barometer reading as BM. At this time, HB, barometer reading. Okay, so that is the only thing, guys, that you're just gonna need here. So it is from the same concept, the density, gravitational acceleration, but this time we're gonna use what? Our HB, which represents the barometer reading. Our barometer reading. So whenever we see these, guys, do not be scared about these. It is still one and the same as we used to have manometer reading, the barometer reading. So even from your formula sheet, wherever there is not MM, you're just gonna write as what? As HM. This one you're just gonna write as what? It's HB. You're done. So from that barometer reading as well, we can determine this in this manner. When we are dealing with the atmospheric pressure, we can calculate it from the same barometer reading, but this time we're going to multiply to 101.325 over 760. Okay, so this, guys, here, it is a conversion. Remember, here we are talking about our atmospheric pressure in what? In pascals. So this here is a conversion. It is the same thing. Also, we can do it, or we can have that for any reading which is taken in what? In millimeters of mercury. We can convert it to the kilopascals by multiplying by this. So this is a conversion from millimeters of mercury to what? To the kilopascals. So we could have even used this one on anyone, as long it is to calculate the exact, even calculating of the gauge pressure. We can do that. It's a conversion to kilopascals. So it is the opposite. When I am given the kilopascals and I want to convert them to the millimeters of what? Of mercury, it means I'm going to multiply. This time it is going to be like this for me to convert, because it's kilopascal. I'm going to take whatever that is in kilopascal, the pressure, which is in kilopascal. I multiply it to, so this pressure, I'm going to multiply it to 760. You use 760 over that, 101.325. So it means whatever that you have here, as long it is in kilopascal, multiplied to this, you are turning it, or you're converting it to the millimeter mercury. So here, that is the it's just a conversion, a simple conversion that we are seeing here. to convert our answer to what? To kilopascal. So meaning to say we have that millimeters of what? Of mercury here for the barometer reading. When multiplied to this, you are turning to what? To the kilopascal. This is what I'm trying to say. All right. So that is it for the atmospheric pressure and the gauge pressure also. This can lead us to the calculation of the most important thing which we want here, the condenser pressure, which is the absolute pressure. So some, they can write that one as PC, or you can just write as P absolute, or you can just write as P. That is the absolute what? The absolute pressure, our condenser what? Our condenser pressure. All right. So this is taken from the difference between these two, atmospheric and the gauge. So we must remove the gauge from the atmospheric to remain with what? The absolute pressure. So as for me, guys, I'm just going to use P. You can use PC, you can use P, absolute, whatever that you understand. I'm just going to use P. So the absolute pressure is from the difference from what we obtained, the atmospheric minus the gauge. Atmospheric minus the gauge. If we are to consider on our calculations, guys, if we are to consider properly from our calculations, the gauge pressure is considered as a negative value. On what we had from the calculation here, remember I said we can have this. I want us to combine so that it can make sense. Let me have this one. I'm now forced to have it. This one for the gauge pressure. We had from this calculation, which is really something to use, working with those densities, guys, it was really to be used. The issue be when you are given that manometer reading, which is the most important case, because they are going to give us that manometer reading. So we can use this as HM. Remember, I said conversion. HM is in what? Millimeter mercury. So converting it to kilopascal, just like this, we must multiply by what? By this. We are now converting it to what? To kilopascal. So by multiplying to 101.325 over 760 is a conversion to the kilopascal at the end of the day. But this is taken as a negative always. It is taken as a negative value. So as it is taken as a negative, we want to combine these two so that we'll see the formula that we end up having from that formula sheet. Now we are saying the absolute pressure is the difference, okay? It is actually we're supposed just to combine, but because this one is carrying a negative, when we combine, when we add them, it's gonna end up still with that negative on the answer. I'm saying the whole of this part, whenever you calculate it, you take it as a negative when you are dealing with what calculation of the gauge pressure, okay? So it was going to be like this: HB times 101.325 over 760, because this one, whenever we calculate it, it gives us a negative, so it was going to be minus HM times 101.325 over what? 760. So this is a common value. Here's a common value, so we can factor it out. So at the end, our P is going to be, we'll be left with what? With the HB minus what? Minus HM times the one that we factored out, the common factor, which is 101.325 over 760. So that is the formula that we see from our formula sheet. which will be given in terms of the barometer reading as BM, manometer reading as MM from our old version of our textbook. Absolute what? Pressure. So this is the one that we're going to have here. From that difference, actually, that is where it is going to end up with. All right. So we saw, guys, where this one was taken from. If we combine those two, because PG is taken as a negative. So meaning to say at the end of the day, our absolute pressure or the condenser pressure can be given as what? As HB. So that is going to be HB minus HM times 101.325 over what? 760. So meaning to say the pressure that we are dealing with is in kilopascal at the end of the day. Remember this thing. So it is in what? In kilopascal. So now the problem that we have with our I don't know what can I actually, how can I put it or how can I express it? The problem that we have with our sources, we have a condition where this time we worked out the absolute pressure, we round off to the nearest whole number. Another case, you see another question paper working with something else, interpolation, which brings confusion even to the students. So for the sake of revision and for the sake of understanding, whenever we've got these decimals that will be on our answers, round off to the nearest whole number. All right, you round off to the nearest whole number for the pressure that is available to from the steam tables. That is, some are decimals. So if you see maybe something is related to 3,5 something, maybe you got something like 3,4, let us just say 3,4 something. We can just take a value which is closer to that, which is 3,5. All right? Instead of taking what? The 3,0 compared to what you have from what? From the steam tables. If you have got a value 5, whatever that you have, it is 5,777 and so on. You round off to the nearest whole number, which is going to give us what? Which is going to give us 6. This one, we could have said we've got a 3. But the closer value, the closer is what? 3,5. So we can use that one. When we have got numbers such as 5,7, you have approximated your answer to the next digit, which is 6. You can use that. Some, they can even work with the 5,5. That one, guys, I won't allow you to work with that one. The lesser, like to reduce the value. It's better for you to get to the next value. From 5,7, what is the next value that you have? So that is where you see now some of the questions. You see question papers, they put uh, estimations. Estimation. So we need to correct that and say for each and every value, just to the nearest whole number, or when the value is closer to the value that you are given on the pressure there. As you are going up, as you are increasing your values, you must consider that one. So that is the most important thing. All right. So when given our pressure, which is the absolute pressure, at that pressure, there are so many things to be considered. Let's say our absolute pressure is 5. From there is what? The temperature There's so many things to be considered from that. Knowing the value of the temperature there, which corresponds. So when you're working with the steam table, you see the importance. You must be able to know everything in that row that is representing the 5. Not to say we are going to use that information, but just understanding to say those are the values that are corresponding to what you are given. So, like I said, from the formula sheet, we can have these values written in terms of BM and MM. So do not be surprised because also we had changes in our syllabus. So we are also hoping for the changes even on the formula sheet. Because if you check, there are a lot of formulas that has been introduced which we haven't updated on the formula sheets now. So that brings you to, as an individual, to know everything. Maybe in your exams, you are going to have something that is already updated. We do not know from the department, but we just hope that it's going to be updated very soon. Okay, so that is it, guys, for the pressure. These ones, you need to know them. The gauge pressure taken as a negative. So that brings to this calculation of the gauge, calculating the gauge pressure when we are given the manometer reading. Take that value as a negative. But when you're calculating the atmospheric pressure, positive. That is the thing. So here I think I wrote it here. So all these we're gonna need them. So here, guys, I don't think there's something that I need to add. Maybe when you're doing questions, we shall see from our questions, guys, question papers and so on. So let's just add also the second part of our calculations, which is on the heat flow. So the first it was on the pressure. Now we need the heat flow, which is actually the heat flow rate as you consider it will be kilojoules per given time. So that is what the heat flow rate. The heat flow rate is taken from the two things that we have from our condenser, the steam. Remember, we have got the part of the steam, and we also have the cooling water. These two, they have the heat which is to be considered. One, remember the steam, it is to be cooled. The steam, as I explained on the introduction video, it is to be cooled by what? By this water, the cooling water. So in terms of the heat, originally, the steam is having a greater value in terms of the heat value, guys. Remember the steam, it's the temperature is more compared to the cooling water. It's lesser temperature. So the cooling water, its heat is actually less. So what is going to happen is that when you are trying to cool this steam, you are reducing its heat. You are going to reduce it. So meaning to say the steam will lose heat. It will emit heat. So from the steam, the heat is being lost. Whereas the water, as it entered with a lesser temperature. When it is coming out with a higher value of temperature. It has gained the heat value. The heat is going to increase. So here it will increase because of what it is meeting with. It is meeting with something that has got a higher value to reduce it. But as it is trying to reduce it, it's not gonna just reduce and come out at the outlet with the same temperature. No, it's not gonna happen like that. It is gonna come out with a higher value of temperature. It has gained the heat. So the water, which is our cooling water, it gains the heat, whereas the steam loses. But at the end, remember the concept of conversion of heat. Energy cannot be destroyed, but it will be converted from one to another. So as this is reducing, it is adding up to the what? To the water. As the water is increasing this value, it has taken something from the steam, but at the end, they must be equal. The heat must be equal at the end of the day. The one that is lost by steam must be exactly equal to the heat that is being gained by what? By the water. So you can even use this illustration for the heat flow rate, of which it's not that much considered in your syllabus, unless if you're talking about the mass. The mass guys must show that this is the mass flow rate that you're given. So this is what you're going to have. So you're going to talk about that later on, the being equal of these two, but let's just consider how now to calculate that heat that is being lost, which is the heat that is lost by steam or emitted by what? By steam. So we have got the heat lost or emitted by what? By steam. By the steam. So I'm just gonna put it this one as QS. So QS is equivalent to the mass of steam, which is the rate, kilograms per unit time. Okay, so let's just put it here so that because we are still on the rate. So your textbook, they can just leave it as QS. It's fine. Do not worry about that. But this is supposed to be what? The mass rate. Rate. The mass rate. Kilograms per what? Per unit time. Per second. Per minute. Per hour. As long it is per unit time. So that's into the difference of the heat enthalpies, which is HS minus HC. So this is going to give us the answer in kilojoules per the unit time that you used here. The time that you used there on your mass. Kilograms per second, this will be kilojoules per second. Kilograms per hour, this will be kilograms per hour. Per minute, this will be kilojoules per minute. So it is going to be just per unit what? Per unit time that you have used here. Kilograms per unit what? Per unit time. So the question now is how to find these enthalpies. The HS for what? For the steam. Remember, I talk about the steam here. So this is for the steam. And HC will be from the condensate now. The specific enthalpy of the liquid, the condensate. Remember, that's a liquid, this one. So, meaning to find these enthalpies, that's the problem. with our textbooks, guys, and also our question papers. I don't know, guys. These guys sometimes I don't know, but let's just see. We have got the mass flow rate of steam, the HS specific enthalpy of what? Of steam, the HC, which is for the condensate. Okay. HS, which is for the steam. From the introduction video, remember I talked about a statement where I said, as we are working with condensers, we are limited in terms of the type of steam that we are going to use, and we cannot have, or we cannot use what? Superheated steam. We cannot do that one. We work with either dry or wet steam. Dry or what? Or wet steam. When the steam is superheated, we cannot have that HS. It's not gonna work. We are limited to for the condensate. It limits to that. So meaning to say HS depends on the type of what? Of steam. Depends on the type of steam. That's where we have to apply our steam tables, this and that. We can have dry saturated. We can have dry saturated steam. When it is dry saturated, our HS will be equal to HG. Dry saturated, remember guys, steam generation, okay? Dry saturated, or it can be what? It can be wet. For wet steam, we are using H wet. So HS is equal to H wet. So that is what we have. And we do understand that H wet is equal to what? It is equal to HF plus XHFG, where we need the dryness fraction. Where we need our dryness, what? Our dryness fraction, and the enthalpy of water, and for the what? For the evaporation. Now, at what condition are we going to take these? When, take note here, when the temperature is given of the steam, when it is given, the temperature, the temperature, which is our TS, when it is given, that is the one that you use here from your steam tables. When you are given the temperature of what? Of T, of the steam, which is our TS. We're just going to take it as TS. Steam is saturated. At that temperature, maybe our temperature is 24.1 degrees Celsius. At that temperature, we are going to use it to find or to determine these values of HF and HFG for the enthalpy of the liquid. We're going to take our HF there in kilojoules per what? Per kilogram. Our HFG as well in kilojoules per kilogram. We use these to determine our H weight. As we do understand, they give us H weight. For the dry saturated steam, you just take direct. There's guys adding these two. It's a waste of time. Say, okay, to get HG is the sum of these two. Yes, you can do that. But already the value is there. At that temperature, you just take the value straightforward. When your steam is what? Is a dry saturated. You just take your answer straightforward. The value of HG is the value of your HS. Remember, I talk about HS for the steam. So that will be your HG. You just take direct. When HS is equal to H wet, then you must take HF and what? HFG, as they are needed on our formula at the end of the day here. So this is what I'm saying. And please here understand me, guys, because that is where we have a problem again with our textbooks here and also question papers, because they are not consistent in terms of what they want you guys to use. Today they use this, tomorrow it's another guy from this is using this, tomorrow is another guy who is talking about interpolation, tomorrow is another guy who is talking about this. So here, be specific. Maintain your calculations. Maintain those calculations. So this is what I'm gonna say. For, okay, we had HG there. For HG, HF, and also this one, HFG. And HFG, use what? Steam tables. So that's where we're gonna use our steam tables at the given temperature, which is steam temperature. The steam temperature. Very, very important there. Yes, they can do this on a consideration that that steam temperature is not given totally. Totally, it's not there. That's when you use the pressure. If they give you that pressure, you use that one. Or the absolute pressure. When you are given the temperature, guys, when the steam temperature is there, don't go to the pressure. Leave it, leave it. Leave it. But for the sake now of our exams and sake of answering the questions, for the sake of progress, if that steam temperature is not given, because they can do that they do not give you, and there's no way for you to have that steam temperature, use what? The pressure. So when the steam temperature is not given, when the steam temperature here is not given, that's when we use what? Use P, pressure. Use pressure, which is our absolute pressure, to find what? To find enthalpies, these enthalpies. Okay, that is what you're going to need. You use the pressure now. At the absolute pressure, or the given pressure, given or absolute pressure. So this one, it will be given or absolute, or calculated absolute pressure, or calculated absolute pressure. The one that you calculated, which is, guys, be very careful here. Don't take this into consideration when the temperature is given. The first thing is to consider, am I having that temperature? Am I having it? The temperature of what? Of the steam. When I am having that, use it to find anything, because it is the temperature that is operating for that steam. So use it to find the HS, which is the enthalpy of what? Of the steam, depending with the type of the steam. Is it dry? Is it wet? Okay, that is about HS. Then we also have HC, as we saw there, of the condensate. All right, so here we talked about HS. We also have what? HC of the condensate. So HC, which is our specific enthalpy of the condensate in the condenser. Okay. Specific what? Enthalpy there of the condensate. We are now talking about the condensate, the liquid that we have there, which is definitely the enthalpy of a liquid, which is water, guys. It's what? It's HF. Remember, that is HF. So, meaning to say, HC is simply equal to HF. HC is equal to HF, guys. We're talking about what? The liquid enthalpy. Liquid enthalpy. That is what? HF. HFG, evaporation, dry saturated. So liquid, 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 HF. So HF must be taken, sorry for that. HF here must be taken because this is the liquid that we are dealing with. So it must be taken from the condensate temperature. So this HF from our steam tables, taken from where? Taken from TC, the condensate temperature. Condensate temperature. All right, which is okay. This one I think is straightforward. But there's this thing now. There's this thing. There's this thing. Remember, I talked about the condensate output. I mean, the condensate and the coolant. When we had the spray condenser in our introduction video, I said, or we saw that actually at the end from a spray or a jet condenser. At the end, you'll be having the condensate and the coolant. The condensate and what? And the coolant there. So, meaning to say, at the exit where the coolant is at T2, the condensate is also at that same temperature T2. So you must take note when you are not given, because they are not going to give you that one. So thus, be very careful about what? About this consideration for a what? For spray condenser. So for, I don't know, guys, I've written a lot of things. I don't know if you're going to follow them. For spray condenser. So for spray condenser here, we are saying the condensate lives at the same temperature as coolant, all right? TC, okay, guys, TC. But I wrote this one on the introduction just for the sake of revision. TC is equal to T2. So TC is equal to T2. The reason being we saw that the condensate lives at the what? At the same temperature. At the same temperature as what? As cooling water outlet. So take note, we are talking about the outlet at the exit. So that's why we're talking about T2. So that's when I have the temperature, I can find the value of HF from the steam table. So this is what I wanted to explain before I added this information. I was saying, let's say a value is not here because we can have direct values. Let's say our temperature is 21, comma 1. This is our condensate temperature. We saw that our condensate temperature is 21, comma 1. I'm just saying. Therefore, you can just straightforward in your steam table. You can see, okay, at that temperature of 21,1 HF. Remember, we said it is the condensate, the liquid. So we talk about what? The enthalpy of the liquid. You take it direct as it is. Because you have what? You have that value from the steam tables. But it is not always like that. Sometimes you are given a value which is not from the steam table. Yes, you can use approximations to say, okay, for this value, that's where now you'll be talking about interpolation, this and that, of which in your textbooks, it's not mentioned. That part is not there. We have the relationship between HF, specific heat capacity of water, and the given temperature. Remember that HF is equal to the specific heat capacity of water times the temperature of water. The temperature of water. So if that is the case, therefore HC as it is equal to HF, we can use specific heat capacity of water times the temperature of water, which is our liquid, which is what? Which is our TC. Because we are talking about the condensate here. So that's our TC. On a condition that TC is not from the steam tables. On a condition that TC is not found in what? Steam tables. Is it on? Is it from? Guys, grammar. Grammar. Still grammar, guys. But that is it. You can use that value of HC, your enthalpy. Guys, enthalpies are kilo joules per kilogram. Kilojoules per kilogram. We saw that from our steam tables. So that is how we can answer our questions onward. We avoid confusion to say in this question we are going to approximate, in another question. Let's just use one thing. So this is the condition that we are going to use when TC is not found in what? In steam tables. Let's consider that and we work with this. That is going to bring us calculations which are valid, and that is supposed to be marked. Okay, so that is it on your value of HC, the enthalpy, the specific enthalpy of the condensate in the condenser. So for TC not found in steam tables, I talked about this. And also there's an undercooling effect. For an undercooling, whenever there is an undercooling TC, because this temperature here TC, we said we can have it for this condition where it is directly given, or we can have it for this condition of a spray condenser where you take it from T2, or they cannot give you direct that, but they give us in a hidden manner. They will hide that one, saying the condensate is undercooled. The undercooling effect. The condensate is undercooled. All right, let's just take for an example, they can say the condensate is undercooled. Is undercooled by, I'm just going to give an example of X degrees Celsius. Under here. From its own, it is telling us there's a reduction in terms of the value from where it was. The condensate from where? From the steam. So therefore, our condensate temperature from the steam temperature, we must subtract that temperature of what? Undercooling. It is undercooled by what? If it is 5, you subtract that. If it is 3, you subtract that from the temperature of the steam. Therefore, that is how we're going to have our TS, which is condensate here, steam. This is the undercooling what? Undercooling temperature. Just like that. So we can calculate TS from there. So that is it, guys. So here it is a basic view or general view of ending up with our QS. Guys, it's not direct where you just gonna, okay, QS, you write the formula, you substitute values, they are there. All these processes must be taken into consideration where necessary. where it is necessary. In order for you to end up with the HS that is needed on our formula, the HC that is also needed on our formula. The only thing that can be direct is the mass rate of what? Of the steam. That one you'll be given. That's the only thing that can be direct. But these, you must consider the steam tables, the H. All right, so that is it for the first part, which is the heat lost or emitted by what? By the steam, which we were talking about here before. Okay, it's only that I removed that part when I was talking to say this must be equal to the one that is being gained by the water. So let's talk about that one of the water. Then we can relate them at the end of the day. All right, so let's move on to the second part on our heat. We also have the heat that is gained or absorbed by water. So that will be our part B. The heat gained, or it is what? Absorbed by what? By water. By the water, which is our cooling water in that case. By the cooling water, also it's gonna be the rate of heat is gonna be the rate. So this is Q water, which in our textbooks they can give you direct like this, or you can put this on top to show that you are dealing with what? With a rate that you are calculating. So that rate is given as we're gonna use the mass of water, the mass rate, the specific heat capacity of water times the change in temperature. Remember, as the cooling water entered, it entered at a certain temperature, then exited at a certain temperature, T2. So that difference there, the difference is the one that we need. The difference. So that's T2 minus what? Minus T1. Okay, so that is it. Given the mass of water, the rate of which this water is flowing, the flow rate, kilograms per unit time, it will affect our heat that is being gained. It is going to be kilojoules per what? Per unit time. So you're going to have this one in kilojoules per unit time. Just like that. So we have got the mass flow rate, the mass flow rate, the specific heat capacity of what? Of water, which will be given in kilojoules per kilogram degrees Celsius, or they can use Kelvin there. There is no effect. Don't change anything, just use as it is. And when it is not given, you use the value 4,187. All right. When it is not given, they can give you a rounded off value 4,2, 4,19. They can give you any other value. But when it is not given, you take it what is 4,187. Then T1, we saw this one from our diagrams, guys, is the water that we have on the inlet. So we've got the inlet and you've got what? Outlet. These are temperatures of what? Of the cooling water. So that is it. We do not have anything special or important on this one, since there is no need for the steam table there. It is direct. We just need the mass, the flow rate. You need the specific heat capacity of water and those temperatures. You are done. So that is it. So the end now is the relationship between those two. Remember, I said in the basics, the relationship. So you're gonna have the relationship between what? Between QS and QW. In terms of there's two rates. Remember, the steam and what? And the water. The heat that is lost is supposed to be equal to the heat that is gained. So that is be our relationship. So you can say total heat lost by steam. Remember, the steam is losing. So total heat lost is equal to the total heat that is gained. The total heat gained by what? By water. So we had our formulas, guys. So that is our QS is simply equivalent to QW. And we saw from our formulas, we already wrote these formulas for the steam, all right, for the steam, mass of steam into HS minus HC. All right, there's another formula which is HS plus, but they do adjustments on their formulas. So that one, guys, I'm not going to talk about it because we're going to have what we call confusion. Confusion, confusion, guys. On its own, the topic on its own has got its own confusion. Then I bring on another formula, guys. It's going to be double confusion. So let me not bring that. I'm just going to focus with one formula, and that we can use to answer any questions. So this will be our relationship, guys, for the steam related to the what? To the water. So this formula can be used to find anything. They can give you the mass of water and ask you to find the mass of steam. We do not know. They can give us this one and ask us to find this. They can give us everything and not given T2 and ask you to find that T2 or to find T1. So I cannot say this is the formula that we are going to use to calculate this. It can be used as the two, they are equal. It's an equation. So anything can be used. So to calculate the mass flow rate of condensing water required or for steam, when we are to calculate these, mostly the mass, the flow rate, the mass flow rate of the condensing water that is required, mostly. But it can be also to calculate T2 or to calculate T1, depending with what you are given. And also the relationship between these two, the mass right of the steam and this one for the water, these two, they can give us the rate of what? The condensate. So it is equal to the one for the water plus the one for the steam. So it is also flow rate. The condensate is also flow rate that we have there. So meaning to say it's gonna be kilograms per unit what? Per unit time. So that's it. So we can have this one and also understand as we are dealing with water, guys, density, water, this and that, volume, anything can be used, guys, those MdV, where I need density, mass over volume, when I need mass, density times volume. All right. So that is the condition. So in our case, we're just going to put it this way. Mass, the density, this one, then volume. All right. Density, density. So maybe I need volume. I can calculate when I have the mass of water over the density of water. I want the mass. I have density and volume or whatever that you're given, guys. We're gonna see with the questions, but for now, just know the basics. Just know the basics. So where the steam table is to be used, we saw it, guys. On what? On QS, the steam. On the steam, there we are going to have a lot of things as we are to consider the steam table. So I think that's the most important aspect of your steam tables here. All right. So for the sake of time, guys, let me quickly write these formulas. These ones, we're just going to use them for the sake of time. Let me just quickly write this one. The third is to calculate the number of tubes required, the number of tubes required, which is N. So the number of tubes required can be determined so many formulas. We can use the volume rate of cooling water, volume rate of cooling water over area times velocity. So this is volume rate, right? Okay. Then let me just say V flow rate, volume, flow rate. So it's a flow rate, this one, cubic meters per unit time. Then we have got the area, which is the cross-sectional area of the inside tube. So take note, it is the cross-sectional area of the inside tube. Of the inside tube, you'll be given that one, as we do understand area from diameter, it's pi d squared over 4. From the radius, it's pi r squared. All right, so that is when you have to calculate, and V is for the flow velocity in meters per second. So this is our flow velocity, meters per what? Meters per second. So that is the flow velocity of the cooling water inside tube. All right, let me just specify of the cooling water. All right, no problem. Inside the tube. Okay. So for the sake of us all understanding, then thus applications and those density thing can be used. Remember, we referred relationship, density, volume, this and that, mass density, volume, that relationship, where it is applicable, use it. Guys, remember the density of water is what? 1000. The density of water is, so when you've got water and maybe there's a need for you to have that density, then use it. Okay, the density of water is 1000 kilograms per cubic meter. That's for water. And so here, that is it. So let's say I want volume, it's mass over density. Let's say I want volume, it's mass over what? Mass over density. Just like that. Guys, that's a play around, isn't it? That's a play around. It's just playing around with your formula there. All right, same N here can be determined from other sources. They use area flow, which is just like what we had the flow rate, but here's gonna consider the area flow, which is the cross-sectional area of the fluid, of the fluid. And we've got the area of the tube times the K-pass. So that is the type of condenser is the one that we're going to affect on our K-pass to say, is it a single pass? Is it a double? So that's direct. I think here we can use it to calculate the number of what? The number of tubes. So there are two formulas, like I said. In fact, there are so many ways, but for the sake of us not having a lot of complications, this is what we're going to use. All right, number 4, it is going to be on the efficiencies. All right, so number 4, we're going to deal with the efficiencies, which in our case, we are going to have the first part, the efficiency of the condenser. So there is the condenser efficiency, condenser efficiency. The condenser efficiency, I just going to write it in short, condenser efficiency. You can write as condenser efficiency. You can write as, just put a C there, like this. So our condenser efficiency, just going to write as NC. So condenser efficiency is taken from the change in temperature for the cooling water over the change in temperature for steam to water. Steam to water, meaning to say, remember the cooling water. Okay, let me put it this way. The change in temperature when the cooling water is entering, it enters a T1, output is T2. So the difference, that the change, T2 minus what? T2 minus T1 for the water. Then for the steam, water to steam or steam to water. All right, whatever that you have there. It is actually the steam minus that one of the water, the input. temperature of the steam. Remember I talked about this TS before here. When we talk about these, there was a temperature of steam here. I think it was when you're calculating that HS. Here, when I was saying when the temperature given the steam temperature. So that steam temperature is TS, the steam temperature. It is your TS. That is the one that I'm talking about there. Okay? That is the one that we are talking about here. Temperature of the steam. 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 T1 and T2 of what? Of the water. This is what? Steam temperature. T1 and T2 for what? T1 and T2 are for the water. The cooling water. The cooling water. The condenser efficiency can be calculated from that. As a percentage, simply multiply by what? 100%. We have got our condenser efficiency. We move on to the other efficiency, which is to be determined as our part B, that is the vacuum efficiency. The vacuum efficiency. All right, so the vacuum efficiency, I'm just going to put a V there for the vacuum efficiency. Oh, it's something they can use a vacuum. It is still one and the same thing as long as you understand what you are writing there. This is another one which is a lot of formulas to be considered. We can calculate the vacuum efficiency from the gauge pressure. Remember I talked about the gauge pressure before? From that gauge pressure. So the actual thing here, it is supposed to be actual gauge pressure over ideal gauge pressure. Let me write it, let me write it that way. Actual gauge pressure, actual gauge pressure over what? The ideal gauge pressure. Ideal gauge pressure is the one that when we say ideal, we do not consider to say there is a loss, there is this, and that is just perfect, like perfect. Of which it must be an adjustment that we are going to make from the steam. We have to get rid of the atmospheric. Okay, let me write it this way. Let me put it that way. So we can have this one, which is, or which can be given as PMG over PSG. So that is actual gauge pressure over the ideal gauge pressure. So this is what we are going to have. Whereas when you just talk about the actual gauge pressure, this is the gauge pressure inside the condenser, guys. Inside the condenser. The gauge pressure inside the condenser, the one that you calculated before this one. You already calculated it. So when I talk about these pressures, when it is pressure like this, it means the units that we're going to use will be kilopascals, kilopascal. We're going to have a conversion. Remember I said this can be converted to the millimeter mercury. So here, this one, guys, our actual gauge pressure is the one that we've already calculated before. Let me just write gauge pressure inside what? Inside the condenser. We already calculated this one before. The one that you were just using as PG. The one that you were just using as PG before. It's only that we are using the M now. So PG, remember, is the one that I said we take it from what? From the manometer reading, and it's always a negative from what? The manometer reading. In a kilopascal is supposed to be 101.325 over 760 that you are using here. For us to have our answer in what? Kilopascal. So that's where we're going to have our PMG and our PSG, which is the one that we are talking about as the ideal. It is the gauge pressure of the steam at entry. It is at the entry, this one. Gauge pressure of steam at entry. So at entry, meaning to say we must subtract, we must subtract, all right, this is SG. We must subtract the one for the steam original because we are saying it is at the entry. So we are supposed to be from the pressure of steam. We subtract the atmospheric what? The atmospheric pressure. So that is the condition. So this is PS. Take note about this PS, guys, from the pressure of steam from your TS, from your steam tables here. This one, it is taken, must be taken from the temperature that you referred back there. Remember here, that TS, this one. From that TS, that is where you obtain what? This PS. This one is from what? From TS, which is the temperature of what? Temperature of steam. That is temperature of what? Of steam, which is not just the temperature of steam, but it is the steam that is saturated, temperature of saturated steam. Because we can have a condition where the gauge, where we are talking about this one being affected in terms of, because we are saying it is the saturated steam, but it can be affected. There are cases also that can affect this TS, this PS, because it is from the saturated steam. So let me leave it for now. I'm gonna add something there because yeah, okay, this is the last part that I'm gonna talk about for today, guys, because there are a lot of things that we're gonna need. We end up having confusion. So I'm gonna end up with this one later on. Let me put it aside. Let us just talk about atmospheric. I'm gonna talk about that. I'm coming back because it has a lot of things to be considered there, and that's most confusion where we even see from our textbooks and question papers. One day they write this, tomorrow they write this, which is something that I hope it's gonna end. Um, it's not gonna happen like that. The atmospheric pressure was already calculated. This one, atmospheric already calculated. Calculated. We calculated this value, remember? From that formula, atmospheric pressure is equal to HB, where we used HB times 101.325 over 760. So just like here for the gauge pressure, here we're going to use what the barometer reading, I talked about that conversion to kilopascal. So the atmospheric pressure is there. You have it already, this one. But PS is not there. It must be taken from the TS as the temperature of the saturated steam. So that alone brings us a lot of questions to say, when this steam is saturated, because we are saying the saturated steam, what is it that we talk about when we refer to the saturated steam? It is the steam that exists at the exact temperature. So it exists at the exact temperature at which water boils at a given pressure. The saturated steam at a given pressure. That is why we are saying from that temperature, we must have a pressure which corresponds to that. And remember about this type of steam that we are talking about from all the calculations we had before. We cannot have superheated steam. That is where the limit now, where I was saying if we are dealing with our condensers, we are limited about the type of steam. We're not going to be using superheated steam. You see, the condition is here. PS cannot be from superheated steam. It is saturated steam. So now there are cases that we must consider to have that. because it's taken from a temperature. What if that temperature is not given? What if the temperature is not given? So let me just have cases, okay, to find PS, which is the pressure of steam. The first case that we can have is when or if the steam is wet. If the steam is given as what? As wet. We can have that because it's saturated. If the steam is what? Is wet. When the steam is wet, use the wet steam temperature because wet steam must be at a saturation temperature. So if the steam is wet, use what? That temperature. Use, all right, use the wet steam temperature. So you're going to use the wet steam temperature to find what? Your PS. From temperature, from your steam tables, remember you can obtain pressure from there. The second part is if the question gives the condensate temperature, you are given the condensate if the question gives you the condensate temperature, which is our TC. They gave you the condensate temperature without wet steam temperature. The wet steam temperature is not given this time. No wet steam temperature given. Be very careful when it is like this. When the wet steam temperature is not given, but they gave us what? The condensate temperature. Use the condensate. That is where you use it. Do not just use it anyway. Just like we saw this one, guys. It's not the first time. Remember, I talked about this when we dealt with the pressure before, when you are calculating that HS, when we wanted to calculate H wet. And we said it must be taken from the temperature of the steam, which is from TS. But when it is not given, then you work with what? With the pressure, which is your absolute pressure. It is the same thing with this one. When the wet temperature steam is given, the wet temperature, the wet steam temperature is there. Why did I write steam? This is steam temperature. Now that I'm writing, I'm calling it a steam now. Say, what is happening here? So when it is given, use it. But when that wet steam temperature is not given, but they gave us the condensate now, we are supposed to use that because the condensate is saturated or slightly subcooled. The condensate is what? Is saturated. Remember, this is saturated steam. So the condensate is also saturated or slightly subcooled. So use what? Condensate temperature. When it is like that, you use what? Your TC to find the value of PS. These are the cases to find what? PS from our steam table. Just like that. So, no superheated steam, PS pressure at wet steam temperature, or we're not given that, but they gave us the condensate temperature. We use that one to find our PS, the pressure for the what? For the steam. Atmospheric is already there. So you see, guys, you want to calculate what? You want to calculate efficiency, vacuum efficiency. But look what you're going through. You have to go through this in order for you to have this. So we shall see in the examples and question papers how to apply this. So make sure that you join membership so that you do not miss any of the videos that we shall be having on our Power Machines N5. In fact, for any other N5 subject that we are having, depending with our time. That's our vacuum efficiency. And as illustrated from this formula, and these are the things that you're going to need. It can also be given, all right, vacuum efficiency, let's just say there are two formulas. So number one, or let's just put this one because we've been writing 1, 2, 3. So let's just say item 1 for the vacuum efficiency. The same vacuum efficiency can also be determined or calculated using this formula. Remember, actual vacuum, from what we had, we're talking about actual pressure here, the actual gauge pressure. It was because we converted, guys, are we seeing what happened here? The gauge, we converted the manometer reading here to kilopascals. Remember that conversion of our manometer reading to kilopascals. We could have used those in millimeters of mercury without conversion to the kilopascal. Without that conversion. So what is it now that we are going to do without conversion? The formula, it'll be the actual vacuum. Instead of saying pressure, we talk about vacuum now. Mercury, from that mercury concept, this and that, over the ideal vacuum, where the actual vacuum is taken from the manometer reading. All right, so for this is the formula that we see from your other textbooks or even question papers using MR over VI. Guys, I'm not gonna change it so that we do not have confusion, because there are already a lot of things that we have introduced. So, all right, this is MR. Whenever you see it, it's just the manometer reading. So it's the HM. This one, it's HM manometer. This is HM, guys, manometer reading. Your manometer reading in what? Millimeters of mercury, because we need that. That is the only issue here, is changing of units. The above formulas was for pressure, kilopascal. Here we are using that mercury values. So we have the MR representing what? HM, the manometer reading. Take note. And VI is representing our ideal. This is the ideal, and the ideal must be taken from the barometer reading, and we must subtract. Remember, it is ideal, just like what we had here on this PSG. We had to subtract it from the atmospheric. There's a calculation hence forth to be made. So it is the same here. Let me just write it and have the formula. So for the ideal vacuum, what we are going to do is to calculate it from this one. We're going to calculate. Okay, let me just put it this way so that we do not mix these formulas from here. These are on their own. So this one, VI, where VI is equal to our ideal vacuum, it is equal to the barometer reading. So this one is the barometer reading, our HB. All right, barometer reading minus, take note on this part that I'm going to explain here. The barometer reading, remember, it's units, millimeters of what? Millimeters of mercury. So we must, for us to subtract here, we must subtract something that is also in the same units of mercury, same units. And any conversion from pressure to the millimeters of mercury, remember I said you multiply by the opposite of what you have been using. You have been using that value with 101 point what over 760. The opposite, you just interchange. So it will be 760 over 101.325. It's a conversion, this one, to the units of what? Of mercury. So that is the one that we are going to use. But which pressure now are we going to use that we want to change its units? It is the steam pressure. When steam is what? Saturated. The PS that we've been talking about here, this one, it is the same PS here, the same PS. Here we are dealing with the pressure exactly. There's no adjustment. Just take your pressure as it is. Here it is because of the units that you are using. So we convert that pressure to the millimeters of mercury. So it will be PS. All right. So it's going to be like this. PS into this, or just times PS times 760 over what? 101.325. So that is what we are going to have here. So this one is just a conversion. The whole of this thing, it is converting the kilopascals steam pressure here to what? To the millimeters of mercury. So that's going to give us the ideal vacuum. So here we are still on the same PS that we talked about before. Same PS, nothing has changed here. So the way that we calculated or determined our PS is not going to change. We talked about this, how to determine our PS from our steam tables. There are two conditions: if the steam is wet or if the quiescent. So the way that you calculated there, nothing has changed. In kilopascals, then you convert it to what? To the millimeters of mercury by multiplying by this. So that is going to give us what we need, guys, which is our ideal vacuum. So bringing these, the HM, which is your manometer reading, and this ideal vacuum, we put it here, we can calculate our efficiency. So take note, I said BR simply represents what? HB, the barometer reading. That's our barometer reading. So everything is direct, guys, direct and straightforward. Steam pressure, barometer reading. Here I've already written this. That's our barometer reading, which is already given, your HB. So in summary of these, as we are to refer calculations and the use of our steam tables, we can say that it is very, very important to note the question that you're given in terms of the type of the steam, understanding the condenser type. We saw what happened when we are dealing with a jet condenser in terms of the output steam, our spray condenser or jet condenser. You saw what happened here. All those aspects, you must put them into consideration so that when answering your questions, you're not going to have any problem. So this is it in our summary, a detailed notes that we can use on our steam tables, saturation pressure PS, on calculating the PS value, which is the one that I will mention here. Saturation temperature and pressure, steam tables, list properties of saturated water and steam. For every saturation temperature, there is a unique saturation pressure. Wet steam always lies on the what? On the saturation line. As long as wet steam is going to be on the saturation line. That is why we use its values for other calculations. It's because of that. Because it's on the saturation line. When to use steam temperature to find PS? When do we use that? The steam temperature. When exactly can we use it to find our PS? We can use this on a condition that the steam is wet, as mentioned before, or wet steam temperature equals saturation temperature. When we are given that, therefore PS is obtained directly from steam tables using what? The steam temperature given. When this happens, use your what? Your steam temperature from your steam tables. You can find your what? Your PS. When do I use the condensed temperature to find PS? Because the condensed temperature, we saw that it can also be used, but not always. You just given a question, you say, okay, this question, no. There are conditions. When exactly can we use it? When to use? Okay, the first thing, use the condensed temperature when entering steam is not saturated. When the steam that is entering is not saturated. Thus, when you are not given the saturation temperature at all, it's not saturated. Not to say, not to say when you are not given actually, but when it is not saturated at all. Therefore, use what? The condensate. Since we said the condensate leaving the condenser is also saturated or subcooled. So you can use the condensate temperature in the saturated water table to obtain your PS, pressure of steam. Temperatures that are not listed in steam tables you can use the closest available temperature. Interpolation not required unless exam demands, unless they specify. Because the problem with interpolation, guys, it is something that you're supposed to know. Actually, you're supposed to know that. But how do you teach someone that is not in the textbook? It is out of the text. That is something that you can actually have an idea about. Because I even saw a question paper, it was supposed to be November 2024. I don't know the person who was even using that memo. They are now putting that, they put that interpolation there. But you revised the textbooks. No interpolation in your textbooks. Exam, you expect a student to use interpolation. No. So it is something, yes, if they demand that, then you're going to use it. But in the basics of your calculation, you must, for an example, you're given 36 degrees Celsius. Let's see, 36 in terms of temperature. From our steam table, you can see there is 34,6, there is 36,2. 36 is not given. So let's say that condition happens, guys. Instead of you to use interpolation, just use the approximate. The table has 36,2 nearer value. So use 36,2 degrees Celsius to find your what? Your PS, the one that you want. Because it is there from the steam table. It is only that our steam tables, they limit. If you find another part of the steam tables, let's say others they are using different steam tables. Other regions in terms of syllabuses or countries, they have that 36. Us, we do not have in our steam table. So we use the next, the closest available, value. And interpolation, unless they specify in the exam, because going throughout your textbooks, guys, there is no interpolation. It's just straightforward. I've been working with TVET first. I've been working with hands-on textbooks. No interpolation at all. They answer direct questions. Direct. So this is the one that I'm going to expect you also as an individual to do. You are going to obtain full marks. Yes, you can use that interpolation. I'm not saying it's wrong. You can use still, because using interpolation, it is having values closer, like you're getting closer to the answer. So okay, this one conversion, I talked about it, that's why I did not use it there. So it is in your hands if you want to go into that. Still, they will mark that one. So the examiners, at the end, they have a lot of work to consider. Power machines, N5. That is why you work this. You see your answer. You check, is my answer close to the answer that is given? If it is close to what is given in Power Machines N5, N6, guys, you are done. It is correct. You move on. My answer is close to the answer that is given. It is correct. You move on. So that is it, especially for these steam tables. The aspect or the review of it or the mind of it is not clearly given to say what is it exactly they want you guys to use. You see the problem. There are so many things dealing with steam table. There are so many things, guys, that we must learn. So the problem now with what I have seen with our textbooks, especially when it comes to exam, they give a question from another regional or maybe country or something, where they are using another concept which you are not using in your own textbook. Then you try to use that concept now to put in the exam. Then you guys will be now confused to say, this question was answered in this question paper like this. I'm doing another question paper different here. They are answering it like this. They are just trying also to bring other ways that you can also view those questions. Not to say there's something that is wrong there. No, it is good. But the only challenge that we have is that all is not listed in our textbooks, what they expect us to know. Even if they revised the curriculum, still they did not add those things that they wanted you guys to use. You see the concept. So anyways, guys, us at Maison African Motives, for the sake of revision, this is what we are going to use, and try by all means to apply it for any question that you're given. You are going to see that all your answers will be exact or closer to the answers that you are given, which is okay like that. So that is it, guys. Like I said, do not forget to join membership so that you do not miss the examples. As you can see, this one is a challenging topic on its own. So make sure that you're part of the membership so that you see all the examples that we're going to have, all the question papers that I'm going to attempt. That is going to help you a lot, using of the steam tables, and so on. So that is it till we meet again.